This is Cosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to the Kosmographia podcast with Randall Carlson. Looking forward to what Randall has planned for us this week. But first, let's introduce everybody as usual. Brad, how you doing, sir?
Hey, good evening. Really good. Really good. How about you guys?
Doing good. Yeah, we're doing good.
Doing good.
We may have a storm coming up on us here, but I think we're going to be safe in the cube. Mike, sir?
Good evening. Good evening, everybody.
Good evening. What's going on with you?
Oh, just a quiet week here. Trying to avoid the Rona.
Flagged.
That's right.
Randall, sir.
Sir, yes,
Have
sir.
we seen that background before that you're showing us there?
I don't know. This is Cade's Cove,
Okay.
which has an interesting story behind it, but we're not going to get into that story tonight.
All right.
But
He did see
beautiful.
it, but he didn't tell us where it was.
Yeah.
North-
Beautiful mowing job, though. I
Yeah.
can see the
Yeah.
mowing is
Cade's
very
Cove is
professional.
in it's actually in the Smoky Mountains
Ah,
National Park. And it was once a thriving community of settlers that created a really interesting community here that was basically forced out of here by the federal government, I guess in the 1930s or 20s when they decided to make it a park. So all the people that had settled this land were forced off and had to leave. And it was quite an injustice for some of the people involved who were basically required to give up everything and just pull up and leave.
yeah.
Yeah.
Wow.
But yeah, there's a much more detailed story that I used to know better years and years ago, but I probably took that picture 15 or 20 years ago. It's really, really a beautiful place.
Yeah, it was probably 2004 or 5 back then. We made those couple
Yeah.
road trips, 2 or 3
Yeah.
summers in a row.
So that's the Smokies in the background there?
Yeah, Cade's Cove is in the Smoky Mountain National Park.
All right.
That wouldn't be some of the larger
Right.
hills. Yeah, there's a region, Cade's Cove, where it's a little more subdued, right? Where the lay of the land is a little leveler and open. And so it would have been an ideal place to settle and start farms because you had this, as you can see there, it's rolling and not so
Yeah.
steep.
Looks like good farmland for sure.
Yeah. Mhm.
So there's like a one-way road that circumnavigates around it, right? And there's
Yes.
herds of wild animals roaming free through there, and
Right.
just scenic little place.
Right. Yeah, I was thinking we would get a group of people together and we would go in there and seize control of the place. And
And we
Make-
should
make
dig
her-
in that place right over there above your right
yeah,
shoulder.
I can see
Yeah.
that. That's definitely a mound right there.
right there, yeah, that was my plan. We'd get a bulldozer in there and no.
No.
I'm kidding. So gosh, we've been learning about microspherules and framboids and magnetic grains. We've been talking about proxies. So what is a proxy again? I forgot.
It's something that,
Stands in for something else.
yeah,
pretty
evidence.
much.
Yeah.
Substitute.
It's a substitute. Yeah, it right. It's not the thing itself. Generally, it's evidence of the thing. It's how. So when you have a bunch of proxies, what you're trying to do is get like a bunch of different things that are all not the thing itself, but all pointing to that thing. And we were differentiating between fingerprints and footprints. So proxies could be either one, right? But we've been looking at the fingerprints, the things that you cannot see necessarily with the naked eye. So we employ a lot of technology, transmission electron microscopy, energy dispersive spectroscopy, and a whole host of other technologies that allow the scientists to not only to see the objects, but also to decipher their composition, determine what elements they're composed of, generally by exciting them by bombarding them with some kind of an energy. It could be like a laser, and then studying the emission of particles. That will tell a lot about the composition of these things, what they're made out of. So I believe we were talking about the evidence, we were referring to getting into the paper by Ted Bunch and others called Very High Temperature Impact Melt Products as Evidence for Cosmic Airbursts and Impacts 12,900 years ago. Does that sound about right?
That sounds right.
Sounds right, yes.
Definitely spent some time on that one.
Yeah, so this was a paper that was 2012. So, of course, there's been a lot since then, but what I'm trying to do, to some extent at least, is look at the chronological evolution of the thinking, and you know, how these ideas were first introduced by Richard Firestone in 2007, how over the next couple of years they were savaged by the critics, how other scientists who either started out as proponents of the theory or even as critics of the theory, but took a look at it and were honest enough to say, yeah, it does look like there's something here. There is this imprint of something that can't be explained by normal processes, which is basically what the critics were attempting to do. So this paper in 2012 was an important paper, and what it did was it showed that there were these objects that indicated that they had actually been subjected to temperatures of close to 3,000 degrees Fahrenheit, because the elements of which they were composed were seen to be melted. So therefore, knowing the melting temperature of these elements, you kind of know, okay, well, it's been pretty damn hot, right? So, yeah, and then we talked about evidence for, I think we just touched upon the evidence for deposition of 10 million tons of impact spherules across 4 continents, right? Didn't we? This was a 2013 paper.
That was the Whitkey paper, I think.
That was the Whitkey paper, yes. But a lot of others too.
And I think you finished up with that saying that now you think that the estimates for that weight would be a lot more because they've
because
they found more
the
evidence,
geographic range of
right.
the material has increased, has expanded since 2013. So in this particular paper, I think just to kind of like go back a little bit so we kind of overlap and pick up, they're saying that airbursts by a fragmented comet. So they're invoking the idea of a fragmented comet or asteroid have been proposed as the Younger Dryas onset, based on identification of an assemblage. There's a good word, an assemblage, a collection of impact-related proxies, including microspherules, nanodiamonds, and iridium. Now, nanodiamonds we haven't really talked about much, but we're going to review another really important paper, and probably not tonight, we won't have time, but there was a very important paper that made a really exhaustive study for the presence of nanodiamonds. After nanodiamonds was being pretty much dismissed, cavalierly dismissed by the critics. So at the time this paper was written, as it says here, these proxies were found distributed across 4 continents at the YDB. And what is YDB? Younger Dryas boundary. Yep. So distributed across 4 continents at the YDB, spherular peaks have been independently confirmed in 8 studies by the time this came along, but they were unconfirmed in 2 others. So the 2 others were basically the papers that we referenced episodes ago. And we went through not all, but a lot of the protocols that were deficient in one way or another that led to the negative results that the critics then used to try to discredit the idea of a comet impact. So anyways, in this paper, in that particular paper, it's as they go on to say, they investigated 18 sites across North America, Europe, and the Middle East. And they conducted a total of almost 700 analysis on the spherules they found using, if anybody wants to look it up and find out more about it, it's quite interesting the way these technologies work, but I'm not going to try to get into that too much. But they used energy dispersive X-ray spectroscopy for geochemical analysis. In other words, to identify the composition of these things, and scanning electron microscopy for surface microstructural characterization. Now, you remember we talked about looking, as we looked at some of the images of these spherules, we saw that they had a unique textured surface, which was because of the surface got melted and then it cooled. So if you can picture this quenching process, as they use the term quenching. So it gets melted, it cools. As it's cooling, it does a slight contraction, and you get this kind of patterned view that you see in there that is indicative of this process of first melting and then quenching, cooling, and leaving this almost geometric pattern. So 12 of those 18 locations, as they say, rank among the world's premier end Pleistocene archaeological sites, where the where the YDB marks a hiatus in human occupation or major changes in site use. Our results are consistent with melting of sediments to temperatures greater than 2,200 degrees centigrade. We converted that to Fahrenheit, I think it was last episode, and discovered it was just a little under, I think, 4,000 degrees Fahrenheit, 3,900 and something. Right. Hot enough that if any of us were subjected to that temperature, we would probably not survive. Our results are consistent with melting of sediments. Melting of sediments, see, so sediments. This is talking about actually melting the sediments of the ground, right? By thermal radiation. Now, if we refer back to Tunguska, remember, aerial burst, tremendous pulse of heat, thermal radiation striking the ground. Remember the Libyan desert glass. Okay, the Libyan desert glass, you've got this pulse of thermal radiation, incredibly hot thermal radiation. Once it intersects the ground, like if it's in the desert region, it's basically, it melted the desert floor and turned it into a sheet of molten glass. Well, that's a very interesting phenomenon. That's not something you see every day.
Yeah, I think not. And how big it was? It's huge, isn't it? Some of those.
Yeah. I don't have the number
areas
in front of me, but I know that Kyle is looking it up even as we speak.
Of course.
Libyan desert glass. The LDG. Yeah, Libyan desert glass, LDG. See, scientists like to condense everything. You know, it helps in the formulas. It's much better if you just have a little 2-letter or 3-letter thing to plug into a formula. So everything, you know, a scoria-like object is a SLO, SLO. Libyan desert glass is an LDG.
Well, we had looked at the map that Mike brought up last time. It's actually on the Wikipedia page.
Yeah.
It's a pretty large area in...
Should give you the square area. Yeah, it's a large area.
Tens of square kilometers.
Tens of square kilometers. Okay. And that doesn't tell us a whole lot.
No.
But there's, you know, remnants, and the remnants are not going to be anywhere near the scale of the original sand sheet before it was eroded over many, many millions of years. I think we found out the dating of it is now estimated at 26 million years.
That's right.
Yeah. Which we found was interesting because that was 1,000 precessional cycles.
Yeah.
Fits in with that. So You don't have the area there, Kyle?
Well, it doesn't. It just shows a map.
Okay. Well, it's not important. We don't need to get off on that.
It's looking to be about, you could call that tens of square miles.
That's pretty intense. Now, the Tunguska event, was a desert, but we can still use that as sort of an analog in trying to understand other things. Now, there was about 200 square miles of forest under the epicenter where the thermal pulse would have been the strongest and most directed to the ground. Tunguska incinerated 200 square miles, hot enough so basically the forest that was there was completely burned up. It was incinerated. So the assumption, I think, there is that those temperatures would have been close to what we're talking about here, right? So that was 200 square miles, although the total forest destruction was over 800 square miles, right? However, where the trees blew down, it was not hot enough. Now, a lot of these trees are burned and have singes, particularly on one side, the side that was facing the blast and the thermal plume, but they did not get incinerated. So you had about 25 square miles of destruction. But within that you had 200 square miles where pretty much everything was just consumed.
And that's what they referred to as the cauldron.
At Tunguska, yeah.
Right. That central, everything was incinerated. Yeah. So then that'd be similar for that desert glass, because things just were molten in that.
Yeah, but Tunguska left a typical, circular or oval shape or a butterfly shape. But this pattern in the Libyan desert is very much a long, almost like a stream. It's a long rectangular shape.
Well, maybe, here's what I'm wondering. If you have an object coming in and is fragmenting, right? So you're actually getting multiple aerial detonations. Maybe that's what's going on here. But, until I really began to read all the papers on it, I wouldn't really know, like this looks like, what year was this map? Does it give a year? I bet you it's.
I don't. Let me look.
I think that was the 30s.
I
was going to say pre-satellite
Yeah.
era. Pre-satellite era.
Oh, yeah.
And probably we've learned a whole lot about the original extent of the phenomena since then.
1934.
1934. Yeah. Yeah. Okay. Yeah.
You don't remember 1934?
Well, I vaguely remembered. I was younger then. I don't think I was fully grown yet. Okay, so another thing, 2.6 is roughly the conversion of square kilometers to square miles. So in other words, if you've got it in square miles, multiply by 2.6 and you'll pretty much have square kilometers. If you have square kilometers, divide by 2.6 and that'll give you square miles. So
handy. Thank you.
Yeah. So, and just remember now, if you're trying to remember, just remember precessional cycle, 26,000 years. Right?
2.6.
One galactic rotation, 260 million years. Right? The length of the quaternary, 2.6 million. Okay. Quaternary. Okay, what's the quaternary? The quaternary period. It consists of two epochs together. I know Brad knows. Putting you on the spot, Russ.
You want me to guess?
No, I'll tell you.
Is this the earliest one?
Quaternary we are in the quaternary.
It's the Pleistocene and Holocene?
It's the Pleistocene and the Holocene, yes.
Okay.
Yeah.
And the Pliocene was part of the Tertiary. And the Pleistocene gave way to the Pleistocene. This was about 2.6 million years ago. And what primarily marks that shift from one geological epoch, the Pliocene, into another geological epoch, and made it dramatic enough that we went not only from a shift of epochs, but a shift of periods. So it went from the shifting of the tertiary period into the shifting of the quaternary period, was the beginning of the glacial interglacial cycle.
Okay.
Yeah. Now, obviously, it's a little more complicated than that, but in a nutshell, that is the main shift that is used to characterize the Pleistocene from the Pliocene. So the Quaternary is the Pleistocene, which essentially started 2.5 or 2.6 million years ago, and then what ended 11,600 years ago. So think about, compared to the Holocene,
which is like half a precessional cycle almost.
Yes, well,
very close.
If you go to the Younger Dryas boundary, it is half a precessional cycle.
Right.
Almost exactly. So, for all of the people that are familiar with astrology, which of course has been degraded by its use in popular culture compared to what it really once was, the age of Leo, which is marked by the passage of the equinox, right? The vernal equinox. So the vernal equinox was transiting out of the age of Virgo, which simply is referring to the period of time during which the vernal equinox was transiting through that particular constellation at spring into the constellation of Leo. And this is generally given in traditional accounts is about 12,900 years ago. And then, of course, the Vedic number that we get is 12,960, which would be half the cycle in idealized terms, and then twice that for a full precessional cycle. Again, in idealized numbers, 25,920. And so then when you look at the model of the great year, as it has been called, as an analog for our annual year, just as our annual year has subdivisions of 12 months and 4 seasons, so does the great year in traditional models divided into 12 months and 4 seasons, right? I think a lot of the people watching this kind of already know some of that stuff, but it's really interesting because I've always been fascinated by the temporal frameworks that we've inherited from past cultures. And what we find here in this case is a temporal framework that is actually amazingly consistent in terms of actual demonstrable events that documentable events that we can actually date. When you start arraying those in a chronological sequence, there's some very interesting correlations between the archaic models of temporal change and the modern models of temporal change. And that was a bit of a digression there, but it's interesting stuff. So
yeah, always a good one.
Always a good one. Yeah. And we can certainly get back into that because I want to get into, at some point, getting more into some of the mythical and traditional accounts. And especially after we've really gotten into a lot of the science here that we're looking at and getting that picture built up. The picture that's now scientific, that's consistent with cutting edge scientific discoveries and thought. Then once we get that model into kind of a comprehensive form, then taking a look at the archaic models. And I think that's when we will find something quite interesting because we will begin to see a lot of correlation, point by point correlation between the two. And this brings us into the realm of geomythology, which again, geomythology and astromythology being related disciplines that would actually look at traditional accounts inherited from anywhere from centuries to millennia ago as actually being vehicles for legitimate scientific information. Particularly like, geomythology, because ancient peoples witnessed geological events. And their experience of these geological events very much colored their worldview, colored their, influenced their religious view, their concept of the universe, their concept of cyclical change, all of these things. So once we are willing to grant that there's a lot more to history than the conventional accounts, and that there may be long millennia of traditions of learning that have been passed down but subsequently lost. This is not the outrageous idea anymore that it used to be. And I think it's going to be a tremendously fruitful time once we start integrating the two, this modern concept of global change with the archaic model of global change. And I think we're going to discover that our insight has gone through a quantum evolutionary leap in terms of our understanding of the world and how it works, because science is leading us directly into a model where the Earth is not a closed system. And for most of the 20th century, Earth was a closed system. And it was, of course, understood that the radiant energy of the sun was an external input. But because of the fact the fiction of the solar constant governed most thinking about the role of the sun during the 20th century, it could be basically disregarded because, well, it's invariant. The amount of solar radiation and the output of the sun is so minuscule that we can essentially discount it. Therefore, we don't have to think in terms of like changing a dynamic sun affecting, changes here on Earth. Well, once you've ruled out the sun, then you've closed the system down. And so now everything is endogenic. Everything is within the system, right? But now we're realizing, no. Earth is part of a much larger system that encompasses the entire family of the solar system. It's not only the sun, but it's the entire structure, the entire architecture of the solar system. It's the solar wind, it's the geomagnetic field and how they interact. It's galactic cosmic rays and how they interact. So we're getting into a model now where we're seeing that Earth is a part of a much larger ecosystem, a cosmic ecosystem. And guess what? When we look at the archaic models in their own quaint way, they are looking at Earth in that context, in a cosmic context. And astrology essentially is a degenerate, byproduct of a whole different way of looking at how Earth interacted with the larger framework of the cosmos. And the realization that, yes, the cosmos, the changing positions of the planets, the Earth relative to the stars, all of these things are actually affecting and influencing what's going on here below. It's a much more sophisticated model or concept of astrology.
Hey, I was going to say that, according to modern uniformitarians, if you see a grain of sand flip over, you have just witnessed a geologic event.
Well, sort of, yeah. Mm-hmm. But see, you got to remember scale and variance. So, yeah, what's happening on the micro scale is also happening on the human scale, is also happening on the macro scale, is also happening on the mega scale. And that is particularly a salient point when we start talking about fluvial hydrology and paleo hydrology and how landscapes were formed by this confluence of various forces, of which water is probably the most fundamental shaping force of the landscapes that we now inhabit. Water moving, water accumulating, water on a vastly different scale. Essentially, we're talking about like oceans of water moving over the landscape. That's why paleohydrologists have had to employ the term Sverdrup to talk about, the scale of hydrologic events, because, normal hydrological terminology, which is used, if you're going to, you're engineering a dam or, you're irrigating a field or whatever, are basically inadequate. When you're dealing about, a flow of 500 million, 500 million cubic feet per second, you have to come up with another term. So you use Sverdrup, which is 1 million cubic meters per second. And Sverdrup was invented to describe this massive scale of ocean currents where you have whole oceans moving, right? So we're now talking about using Sverdrups to talk about water flows over the land. And so we're going to be segueing from what we're talking about cosmic imprints when we start looking at terrestrial responses. Yeah, then what? We're going to have to be looking at paleohydrology.
How do you spell that term?
What term?
Sverdrup. Or what's
SV Sverdrup. It's kind of a
Yeah.
SV Sverd. Did you find it?
I just
a
wrote
Swedish
it down.
term.
He's taking notes.
Oh, okay. Sverdrup. And I don't know, who came up with it or what year it came up. This I don't know.
Randall, Victor Baker was one of the early researchers into the Missoula floods there that did some of those hydrologic equations, right? And he had one of the papers I remember where he talked about the planetary scale movement of water.
Yes, that's one of my favorite quotes.
Absolutely, that really got
Yeah.
me thinking after being out there for multiple trips to try to imagine planetary scale movement of water.
Yeah, and that is literally, without hyperbole, that is what we're talking about here. And again, we're not talking about a universal flood in the oversimplified evangelical Christian biblical literalist models that requires a supernatural intervention. We're not talking about that, right? We're not talking about simple regional events that, might have not been much greater than, a catastrophic flood we've experienced in the last century or two, right? That somehow got exaggerated in the telling, which is kind of one of the things. Oh yeah, well, it was, Noah's flood was a regional flood in the Tigris-Euphrates Valley, and as it got told and retold, each time it got told, it got amplified more and more, and then pretty soon it turned into it's not that either. But what we are talking about is, as Brad just said, planetary scale movement of water. We're talking about, massive areas of the Earth's surface being drowned for short periods of time under literally, hundreds or thousands of cubic miles of water.
You were just saying using the mnemonic device of 26 or 2.6 million.
Mm-hmm.
A Sverdrup, Kyle just looked it up, is 260 million gallons per second.
No kidding.
No kidding.
Mind blown.
60 million gallons per second.
So is that relationship that you were calculating there before with the square miles, square kilometers, or square miles?
Yeah.
Well, we're talking about shifting, from cubic meters to cubic gallons. I would have to think about that for a minute.
Yeah.
Yeah. It says it's one Sverdrup is equal to 1 million cubic meters per second, or 260 million U.S. gallons per second.
260. So there again, we've got
the 26.
Obviously,
cool.
It's all part of the cosmic plan, right? Somebody thought this through really carefully.
Well, that's a tangent I was going to go on, but since you went on your own tangent, I won't go there. But just the geometrics of the phi relation between a kilometer and the mile. So
Right.
so the 2.6 is phi squared, basically.
Basically, yeah.
So there's that golden ratio, divine proportion going on within all these numbers that are showing up in these cosmic cycles and everywhere else.
And that kind of makes an easy mental conversion, if you're trying to transition from kilometers to miles or miles back again. Just remember 1.6. So
2.6.
1.6 would be your
2.6 or 1.6.
Well, miles to kilometers and back would be 1.6. So,
all right.
So in other words,
0.6 to 1, and then 1 to 1.6.
Okay, so square miles to square kilometers is 2.6.
Yes.
Okay.
Yes. So if you've got, very simply, 10 miles is going to be 16 kilometers. Not exact, of course, but it certainly puts you approximately close to what it is.
Which is also really interesting because
10 kilometers is going to be 6 miles.
Exactly. Yeah. 10 kilometers is going to be 6 miles.
If you drink 26 beers, it's called a swerve drop.
I did not know that. Okay. So, let's get back to what we were talking about.
Are we in break time zone here, perhaps? Or
I mean, yeah, we're at 36 minutes. We could take a break
before we jump back in deeply.
Okay.
It is a good break time.
Okay. Geez, I thought we'd only been like 5 minutes or so. I start having fun, and
Yeah.
I lose track of time.
All right, ladies and gentlemen, we're back. And I guess we're moving back into the Whitkey paper. Is that correct?
Yeah. So in this paper, they are talking about the 8 studies that seem to have confirmed the presence of impact proxies, and then the 2 papers that didn't. The paper by Suravel and Pintar that basically were very dismissive of even the possibility. Referring to it as one of the papers, I think by lead author Pinter was, the Younger Dryas impact event, a requiem. Like they were in that paper, they were just going to basically put the thing to rest once and for all, get this heresy out of there so we can get back to our standard models. We can go back to the idea that the humans, killed off the megafauna, especially because that has political implications and so on and so forth. And I'm not necessarily saying that was a motive of those guys, but that's certainly part of the academic structure of which they are a part, which is basically maintaining this standard model, right? And that standard model has certain assumptions about a lot of different things, particularly having to do with the impact of the human presence on Earth. And if we are indeed engaged in a triggering the 6th great mass extinction in Earth history, this is serious, and we need to really address our actions. And if we were, in fact, responsible for the extermination of the great megafauna at the end of the last ice age, then that is prima facie evidence that we are capable of such a thing, and not only capable, but willing to do it and have done it, right? So we will most definitely be taking a more in-depth look at the so-called Great Five, which are the 5 most intense, powerful upheavals in the history of the planet and life on Earth. I think they're important because of what we can learn from those. So we are going to we'll probably devote half to a full episode on each one at some point, so that we've got down, here they are. Here's an analysis of the Great Five. By understanding the effects, the consequences of those events, that will then give us the perspective, I think, without which we can't really assess what's going on now and our particular role in affecting global change. But when you begin to look at those Great Five, of course, what you discover is that the severity and intensity and the power of those events are on a scale that is almost impossible to even imagine. So will be coming up at some point. Anyway, so back to the Whitkey paper. They're looking at these 18 sites. They performed 700 analysis on these spherules, and as they said, their results are consistent with the melting of sediments to temperatures greater than 2,200 degrees centigrade by the thermal radiation, one, and the other by air shocks produced by passage of an extraterrestrial object through the atmosphere. They are inconsistent with volcanic, cosmic, and when I say cosmic, I'm just talking about they're using the term to represent just the slow, gentle, consistent rain of small microparticles that descend to Earth every day. But of course, with no virtual, awareness on the part of people or anybody, because it's such a minuscule phenomenon. But they do. I mean, there are cosmic particles that regularly rain down upon the Earth. But of course, they don't trigger anything catastrophic. So they're saying that the are these proxies that they're finding are inconsistent with volcanoes. They've looked at that, and they're not the same. The cosmic, they've looked at that, not the same. Anthropogenic, they've looked at that, not the same. Lightning, they've looked at that. You know, lightning can produce fulgurites, right, which are lacatellarite, right, which are very similar. But there's also very distinct differences, and we haven't talked about those, but there are, and they've looked at those differences, and these things are not consistent with something produced by lightning strikes. But you do have to wonder, you know, if lightning strike would cover 4 continents. Now, I know the Electric Universe people are probably going to imagine such a thing, but there is really no consistent, coherent body of information that would support an event like that, right? However, we do know that there are comets. We know that. Comets break up. They produce byproducts. They produce swarms of debris. Those swarms of debris eventually are meteor streams. Earth crosses those meteor streams. Those things hit the Earth. We know all that, right? So we can't just sidestep all that and invent an exotic alternate explanation, because all of that is well documentable. You can find the meteors. You can find the pieces of the meteors, right? Well, we're not going to get into that, but so also they're inconsistent with authogenic. That's spelled authigenic, authogenic, which basically means formed in place, right? So it's the things that they're finding are inconsistent with all of the alternatives. That's the point. So they say at 12.8 thousand years ago, an estimated 10 million tons of spherules were distributed across 50 million square kilometers. So 50 million would be, what they say, divide by 2.6. That would be right at about 19 million square miles. Now, as we said, this is in 2013. So the geographical range of these of this phenomena has been extended since then. Well, then I think that we would have to also likewise expand the mass of this material that was distributed over the Earth accordingly. So goes on to say that impact-related spherules have long been considered one of the most distinctive proxies in support of an impact hypothesis. However, despite increasing evidence for YDB peaks in impact spherules, their presence and origin remain disputed. In the latest example of this dispute, Boslow et al. Stated that, quote, magnetic microspheral abundance results published by the impact proponents have not been reproducible by other workers. Now, referring essentially to the study by Soroval, which has been quoted over and over and over again, right? However, end of quote, have not been reproducible by others, end of quote. Okay, we have been saved from the heresy. Send out the presses to say that, we've been saved from the heresy. The impact hypothesis has been discredited, so we don't even need to think about that. Now we've averted another intrusion of the cosmic domain into our daily lives by suppressing, by getting rid of this idea that Earth might have been impacted on a major scale a mere 12 or 13,000 years ago. Okay, end of quote. However, as Whitke and his colleagues go on to say, the authors, referring to Boslow and others, neglected to cite, conveniently, 9 independent spheral studies on 2 continents, shown in Figure 1, and I think I have Figure 1 here, that reported finding significant YDB spheral abundances. As summarized in high-profile, previously published paper by Israed et al., Bunch et al., and Lecomte et al. The 9 additional sites are located in Arizona, Montana, New Mexico, Maryland, South Carolina, Pennsylvania, Mexico, and Venezuela. Now, that's where they had been found as of 2013. In response to such claims, we here present the results of one of the most comprehensive investigations of spherules ever undertaken to address questions of geochemical and morphological characteristics, distribution, origin, and processes involved in the formation of YDB spherules. They then go on to say, in another study, Pinter et al. Claimed to have sampled the YDB layer at a location, quote, identical or nearly identical, end of quote, with the location reported by Kennett, who did one of the first studies, in-depth studies on the spherules, as part of 3 studies that reported finding no YDB spherules or nanodiamonds. However, the published universal transverse Mercator coordinates that were in those papers, right, reveal that their purported continuous sequence is actually 4 discontinuous sections. These locations range in distance. Now get this, okay? So here's the Kennett team. They go out, they sample the Younger Dryas boundary at this particular location. They go through all the protocols that we talked about before, all of those very stringent protocols that you have to follow. We went through, I think, 4 or 5 different deviations, right? Here's the main one we didn't even mention. Okay, as Whitkey and his colleagues are pointing out here, the published universal transverse Mercator coordinates reveal that, as far as the Pinter study, their purported continuous sequence is actually 4 discontinuous sections. These sections range in distance from the site investigated by Kennett et al. By 7,000 meters. So 7,000 meters, that is over 4 miles away. Okay, so here's the site. They're going to go in there and extract this. This is 4 miles away from the site that Kennett took his samples from, where they found microspherules and nanodiamonds, right? The other 3 sites that they used, one of them was 1,600 meters away, one of them was 165 meters, and one was 30 meters. So basically 100 feet away, right? Furthermore, this sampling strategy raises questions about whether Pinter et al. Sampled the YDB at all, and may explain why they were unable to find peaks in YDB magnetic spherules, carbon spherules, or nanodiamonds. Well, yeah, so if you're looking in the wrong damn place, you know, and again, as we talked about, you know, this is a very thin layer where these things are concentrated, right? So your aliquot has to be adequate, or your, you know, because these things are going to be measured in parts per billion, right? So if your sample is too small, you might overlook it, right? Then the sieve size, remember the sieve size, because these things are very tiny. So you've got to use a sieve with very small aperture in order to filter those things out, because it's the idea, you know, if you're looking for a particle and it's hidden within a mass of a couple of hundred other particles, it's still going to be a hell of a lot easier to locate than if it's in a pile of 10 or 20,000 other particles, you see? So the sieve size was a big factor. By not, you know, concentrating the microspherules to densities enough that they could actually be found. So that was, you know, another factor in why they did not find the microspherules. Okay, then they published, said we were not able to see here, and here's how it worked. We were not able to replicate the findings of Firestone and Kennett and others. And interestingly, and I think I've got it right here, I might pull it up in a minute if I run across it, which I might, but you see some of the headlines in some of the mainstream media saying this: experts disprove cosmic impact. No, literally, that's what the experts have come in and they've weighed in and they've disproven the impact hypothesis. Mainstream media for you, right?
As though Kennett and those guys are not experts.
Right, as if Whitkey and Bunch and Mahaney and
not
all of the rest of Firestone, all of them, they're not experts.
Right.
Yeah, I mean, come on, God. Okay, so they go on to say the analysis of 771 YDB objects presented in this paper strongly support a major cosmic impact of 12.8 thousand years ago. This conclusion is substantiated by the following. Spherules and SLOs, which are the scoria-like objects, and we may have not talked about those, but we can come back to those. The SLOs, SLOs, scoria-like objects, also a result of heat. Okay, spherules and SLOs are widespread at 18 sites on 4 continents. 2, display large abundance peaks only at the YD onset at approximately 12.8 thousand years ago, are rarely found above or below the YDB, indicating a single rare event, and 4, amount to an estimated 10 million tons of materials distributed across 50 billion square kilometers of several continents, thus precluding a small localized impact event. They are the morphologies and compositions of these spherules are consistent with an impact event because 1, compositionally and morphologically similar to previously studied impact materials. Okay. They closely resemble terrestrial rock compositions, which shows that whatever this energetic process was, it was able to inject large amounts of continental material into the atmosphere. Okay. Often display high temperature surface texturing. They can then also, the silicon dioxide inclusions, which is lachatellurite, they're often fused to other spherules by collisions at high temperatures. We looked at some of those images last week, didn't we? I think
We did.
Occasionally display high velocity impact cratering.
I have a question real quick about
Yeah.
the idea that these objects are terrestrial in composition, but we're also talking about the idea of air bursts. So
Yeah.
does that mean that the air bursts are being caused by terrestrial-like objects, like that their composition is also terrestrial-like? Like, I know it wouldn't be the same.
Well, yeah.
Or we're looking at it. We're looking at both, basically.
I think we're looking at both.
Impact.
See,
okay, yeah.
I think what we're ultimately going to see here is that, and one of the legitimate criticisms of the critics is they're saying, wait a minute, on the one hand, you're saying it's cometary, on the other hand, you're saying it's iron, on the other hand, you're saying it's chondritic. Come on, you guys, you can't make up your mind, so get out of here, I think what we're looking at is an encounter with a heterogeneous swarm disintegrating from a comet whose nucleus is anything but homogeneous, and the byproducts of that disintegration are running the range, the compositional range. And so we're looking at hundreds, perhaps thousands of impacts on multiple scales, which could include air bursts, land impacts, oceanic impacts, and glacier impacts.
Right.
So once you start, and this is really, if you have if it's a swarm, and Earth is encountering a swarm, yeah, you're going to expect, just like it says here, they're finding this stuff distributed over 50 million square kilometers. Now, question is that going to be the result of a major localized impact event and then the distribution of the impact proxies, say, by atmospheric transport? Could be, particularly when you're dealing with the scale of this. But what you would have to do is find other proxies. For example, if you find melted rocks there, let's say in Syria, well, that's not going to be from an impact over North America.
Right.
You might find microspherules there that might have been transported through stratospheric currents around the planet and then, precipitated out. Yeah. But you're not going to find you're not going to find the full suite of proxies, and including evidence of, scoria-like objects, again, also display evidence of being subjected to extremely high temperatures, just like the microspherules. I'm going to pull up a screen image here of some of the images of various spherules that have been found at these different sites around. And let me go back to this, and we'll do screen share. Here we go. Now check this out. Look at these guys. Now here we've been talking about Abu Herrera. Abu Herrera. Here, Arlington Canyon, we've talked about that, somewhat that area. We've talked about, Firestone did a paper. Now, this Barber Creek one is interesting because here you can really see the effects of the surface melting. You see that? See how it's kind of globular and
pooling texture.
Pooling,
there,
yeah, exactly. Yeah. And look at Big Eddy. So now here you had two spherules that were in a molten state that collided, and they welded together. And then you look at Blackville. Here's a cross-section of a spherule that has all these inclusions of other things that were presumably entrained during the molten state. Look at this one at Blackwater. Okay, so here's one that actually, it's got a big chunk blasted out of it because it would have collided with a piece that then actually caused fracturing of it. And then the Shobot, if that's how you say that site, here you see the quenching texture where the surface was melted and then it cooled. And so you get these stress lines forming as the material cools. Let's see. Yeah, look at Kimball Bay. Look at this. So let's see. What does it say?
Some of those almost look like like they had an air bubble in them that burst.
Yeah, that's what it looks like. Yeah.
So
these are scanning, as it says, scanning electron microscopy images illustrate the wide variety of sizes, shapes, and microstructures of YDB spherules. Diameters are in yellow. This is EDS's energy dispersive spectroscopy, compositional percentages corresponding to the letter designation of these 36 YDB spherules are in the appendix. Most spherules are rounded, but there are also dumbbells, like Big Eddy. And in fact, sometimes you can get a really dumbbell where apparently they collide together, they're still molten, and then they start to separate. So the handle of the dumbbell is actually elongated, much more than what you see right here. So typical D is bottle. They're calling H is bottle shape. Yeah, here we go. Look at H, a bottle shape. They're calling bottle shapes. J is a gourd shape. P is ovoid. See that? It's not spherical. It's ovoid. Most small spherules are solid, although a few are hollow, such as F and J.
They are hollow.
Whereas most large spherules are vesicular and or hollow. And he's mentioning A, E, and okay, so these are some vesicles within the molten. That's what that is. So those are like just gaps. And M, yeah, look at M. That's from Melrose. So Melrose is the site in Pennsylvania that I want to get into and talked about. We may not have time to get into it tonight, but something coming up very interesting will certainly be our next talk if we don't talk about it tonight. A large number of spherules were cross-sectioned. All others were analyzed whole. Lachateliorite and flow marks, which are called schleren. Like this is schleren, flow marks on the Barber Creek spherule here. Flow marks. And the German term for that is schleren. SCHLIREN. Okay.
I think that would be Schlieren.
Schlieren. I like that
German because the IE would end in the long E sound.
Yeah, there we go. Schlieren. So the Schlieren that formed at more than 2,200 degrees centigrade were observed in spherules from three sites, A, E, and M. So A, so right there, that's probably telling us that there was something localized around Abu Herrera.
Right.
And E at Blackville, and M, Melrose. So Melrose, that's Pennsylvania. So that's Brad's backyard.
Yeah, I have to say, anyone who's just listening to this, the audio version, you really need to go check this picture out because this one is really really good for the spherules.
Yeah, yeah. And then you also have micro cratering by smaller spherules, as on Q. Look at this. And look, see, there's a crater there. And then look at the smaller spherules that have collided with the larger one and then
Yeah,
become
welded to
welded to it.
Yeah, that is really cool.
Isn't it, though? Some spherules
What about the size? Does the size indicate anything in terms of nearness or far away from the event itself? Because I see that their Blackville is that's 1070.
Yeah.
And then Melrose is 760, but some of these other ones are really small.
Yeah, and I'm not sure.
Is there any uniformity of size in these spherules? Are they within a range, or they're just wildly all over the place?
Well, I think what you're seeing right here is the range. You look at the smaller ones here. What's the smallest one? 25 micrometers. And then the largest is 1070. So that probably
millimeter. Yeah.
No, that's not millimeter.
1,070 micrometers.
Yeah. Yes. So that's 1,000.
1 millimeter, right?
A millimeter is 1,000th, and a micrometer is a millionth.
A millionth of a meter, so it's 1,000th of a millimeter.
Yeah.
Yes,
Yeah. Yeah, I didn't hear you.
So that's 1 millimeter there, plus 70 micrometers. Yeah.
Yeah. This, right. Yeah.
I was checking that the other day to be sure, because I said that to someone that it was a millionth of a millimeter. I was like, wait, that's not right. It's a millionth of a meter.
Yeah.
1,000th of a millimeter.
Right.
So that Blackville one is actually 1.07 millimeters. That's what you're saying.
There you go. That's what I'm saying.
And and then this one, I'm not sure where this was. Omen, OMMEN. But there you see the melt and quench texture, which shows up good on the Showbot site. Also, you see it on the Lamel. And it's clearly the Schlieren. Thank you. I forgetting that pronunciation correct. And then, let's see, since we're here, oops.
There's lots of E's and I's, or I's and E's in German, and you always pronounce the second one, which when they're together, it's always the second of the
That's
I.
right. The second letter is long.
Right.
The long sound.
Okay. So here, these graphs basically show the stratigraphic distribution of each of the sites we just looked at, where we saw sample representative microspherules from each of those sites. So if you look at these, I mean, you'll see that, down the left, the y-axis is your depth in centimeters. And, then the x-axis varies depending on, I think, the site. But the point is this will be, let's see, it'll give you the lower x-axis in number per kilogram, okay, relative to the YDB depth at 0 centimeters. Okay, so then scoria-like object concentrations are the black lines and are plotted on upper x-axis in grams per kilogram. Thickness of sample containing the YDB is indicated by the blue bar. So yeah, so here this is the Younger Dryas boundary right here, this bar, and you can see at each one of these, you have the abundance of spherules, which is what we're looking at now, is the red. So boom, boom, every one of these, you see there's just a huge spike relative to the background amount of the spherules during this narrow Younger Dryas interval right here, every single one of them. You see that? Now this is the studies of 8 independent teams, 8 separate teams that have come up with this data. So I would say at this point the idea is pretty robust at this point. That we're looking at something. We don't know necessarily exactly what it is, but we're looking at it.
But Bosler couldn't find it.
No.
That's right. I have a question about that. It's a little off topic, but the thickness of the YDB, what does that mean? Like, if we're talking about proximity to a site, like we were saying earlier, Abu Huraira, could have been one that's very close to an impact, and there's new data showing that. But look at the thickness of the boundary there is so tiny compared to like Blackville.
Yeah.
where it's much thicker. What does that mean?
Well, because your depositional environments are not going to be uniform all over the planet, obviously. There could be so many different factors affecting, the accumulation right at that particular boundary that, who knows to go what that would involve.
I'm curious about just one, like what's one thing that would make it be different?
Fluvial
I don't know.
deposition.
Okay.
Yeah, layer erosion.
Yeah, the
It's
amount of
layer
erosion,
rainfall.
Yeah. Let's say Abu Huraira started out much thicker, but then before you had erosion that, took a lot of it away, and then that was followed by more deposition. Let's see. So at Abu Huraira, the Younger Dryas is at, what is that? About 200 centimeters below the surface. Right? Does that make sense?
Yes.
Okay, so how much did I say? 200 times 200. So that's about 6 feet, I believe. About 6.5 feet below the surface. But over here at Arlington Canyon, it's only 40 centimeters below. See that? And at Barber Creek, it's only 10. Right? So how deeply is it buried? There's so many factors here. How long was that land surface exposed before it was buried? Because at some point when these microspherules were raining down, this was the land surface, right? So
that's right.
Any number of processes could have played out. And what you'd have to do is go to each individual site and pretty much, analyze each site independently to determine, and look at the stratigraphic layers that are above. If you go to the Big Eddy site, okay, so you're 30 centimeters above the, below the surface, right? So that's pretty close to the surface. So
yeah, I think I'm seeing now, I'm realizing that the vertical scale there is so different from site to site that the thickness of the YDB is dependent on that scale.
Right.
So it's actually, they're all very close to being the same, probably.
Well, like here, the YDB is,
isn't it showing at 13?
50, so this is 25. So here, almost 50 centimeters of sediment is the Younger Dryas. Right? Now, however, there could have been processes that would have caused a very rapid buildup of sediment, even instantaneous. You see, in other places, again, there are so many geographic variables that, you would have to, again, take each one of these individually. And for the most cases, what you'll do, if you go into the paper, take any one of these, the Big Eddy, any of them, they'll have it, they'll show the stratigraphic column, and they'll show what's in there, change from, marl to sand, from sand to gravel or whatever, the soil layer might be an organic soil layer. So you can go through each of those and you'll find that, the depositional environments are going to be, and erosional environments are going to be very different from each of these sites. Because again, these sites are, dispersed over 50 million square kilometers. So it could be any number of things. Is it a site on a flat ground, or is it a site on a hill, side of a hill? Is it a site where, is it a desert site? Like Abu Huraira, what might be more like a desert site, or Melrose, where it's a lot of forests and trees. So, again, and if you've got plant roots coming down, that can affect things. One of the things is that cosmogenic nuclides, which can be used to identify the Younger Dryas, they can be taken up by plant roots. So if they're taken up by plant roots, they can end up getting redistributed much higher above the actual layer itself. So again, my point is that there's numerous different kinds of processes at work in each one of these. You'd need to look at the stratigraphic analysis of each one individually, and you'd find out that, so at one point there was a flood that came in here. Oh, look, there was 2 floods, or whatever.
And also, visually, these graphs are just, each one scale is different. Like Barber Creek is 10 centimeters to minus 10.
Yeah.
but Abu Huraira is 200 to minus 200. So the scale on each one is different, just so that they can sort of put it out in this way. So I think that's what Kyle was noticing, is that the scale of each graph is sort of based on its own. It's got its own scale, so you can't really look at those bands and tell anything.
Yeah, but it's still. I appreciate the explanation, because I mean, that's
Well, the point here is that you're seeing the peak abundance compared to the background. That's at each site, and that's what it's attempting to show you.
Yes. That's why I said the question was a little off topic, but I appreciate it. So thank you.
Yeah. Okay.
I think if you looked at them independently, they would be even broader than what you're seeing here.
Yeah, it could be. Yeah. So again, here it is. Thickness of the sample containing the Younger Dryas boundary is indicated by the blue bar. So, okay, so now you've gone down and you've extracted typically a core, or you've got a cross section, and you take a sample in order to capture the Younger Dryas boundary. Now, also, maybe the guys who took the sample at Abu Huraira took a narrower sample than the guys who took the sample at Blackville. So that's a variable.
Okay, yeah.
And then you'll also see that there are variability in the dates. Of course, that could also be attributed to a number of factors, but they're all close with some outliers. Look at the Barber Creek date, 12.1. Now, most of the rest of them, you got 12.9, 13.0, 12.9, 13.0, 12.8, 13.0. But then look again at the Gainey site, 12.4. Right? So there's some outliers in here.
Both of those outliers have a plus or minus, which is, that's always going to be the case. They never can know exactly, there's going to be a standard deviation. Or
so if you add 0.70 to this, then you're right in the ballpark of the others.
Right.
But, so the, let's see, are plotted on the upper x-axis. Yeah. So up here in some of them, here you've got the black line, the black graph line. So that's at that one, they also measured abundances of these scoria-like objects. So the abundance graph is on this upper x-axis up here. But you can see here, Barber Creek, look at here. Here's number per kilogram, okay? So here at Barber Creek, they really found a lot of them, 1,000 per kilogram, right? So that was
Kutio is 2,000. Right?
Yeah, so very abundant there. Yeah, so it's interesting to study these graphs. But essentially, what you can take away from this is each one of these graphs at each one of these sites studied, there may be quite a bit of variation relative to each other, but relative to that site, what you see is that there's a sudden spike of microspherules considerably above the background abundance, either just before or just after the Younger Dryas. And then here's a close-up of the Q, which was, Talega. And so here you can see a close-up of how the smaller spherules have become welded to the bigger one.
I just wanted to add to that last one that, one of them's in the bottom of a lake. The ones that are so, the volumes are so high, one's in a lake and one's in a bay. So you're getting deposition from
Good point.
Okay.
Yeah, Lake Kutio. That's from a core sample taken from the bottom of a lake.
Right.
Yeah.
So you got a lot of different environments going on there, and that I think kind of should explain it somewhat there, Kyle.
Yes.
Right. Okay, so the origin and provenance of the spherules and magnetic grains at the Younger Dryas boundary, the Wu paper, Ying Shi Wu, Mukul Sharma, Malcolm Lecomte, Mark Dimitrov, and Joshua D. Landis. Now, Brad and I know Lecomte and Dimitrov. They were at the roundtable we did in Wilmington. And we had a great weekend with those guys, getting to tap into their knowledge. Dimitrov is one of I think you could call him one of the world's foremost experts on permafrost. And he and I had some very interesting conversations about permafrost. Permafrost is very good. It's a preservational environment. So we find a lot of things. And we're going to be looking at a study that has analyzed some of the Alaskan permafrost layers, and guess what they found? Exactly a whole slew of impact proxies. And this is relatively recent, very recent paper, and very interesting stuff. So the origin and provenance of spherules and magnetic grains. This paper was 2013, and they looked at a number of different areas. One of those was the Melrose, Pennsylvania, and we will get into just a little bit of their stuff and then pick up on that next week. But here's what they say about the Melrose. The Younger Dryas boundary site at Melrose yielded small magnetic spherules as well as large spherules. The latter are enriched in osmium. So now here we have another one of the PGEs or PGMs, osmium. So now we've got platinum found in Greenland ice cores. We'll find out that we're going to be also looking at another study where they find iridium, and now they're finding osmium. And have osmium 187 to osmium 188 ratios that are in general much lower than those of the bulk sediment. Detailed petrochemical analysis of the objects indicates temperature of formation more than 2,000 degrees centigrade, consistent with an extraterrestrial impact, as also inferred by reference 20. And then reference 20, I would suspect, is, yes, the Bunch paper that we've just been talking about. So this is very much a continuation of what Bunch and them were doing. But their conclusions, and we'll look into this in a little more detail because we're going to refer back to something interesting that one of our participants suggested to us regarding Lake St. Jean up in Quebec. And we'll get into that next week.
All right.
I think we may have a potential impact site, which of course is one of the critical factors that the skeptics, the impact skeptics have said, well, you don't have craters, you know, at least with the Cretaceous Tertiary, you eventually produced a crater. So once you produced a crater, we threw up our hands and said, okay, yeah, the asteroid probably played a huge role in taking out the dinosaurs. But you guys don't have a crater. Well, then, of course, there's the discovery of Hiawatha. Problem with Hiawatha, though, is that the dating isn't precise enough to say for sure. And I don't think anybody's going to come out definitively and say Hiawatha is Younger Dryas boundary. It could be. But, again, I don't think we have enough dates to conclusively assume that it is Younger Dryas boundary. It could be. So we're holding, we're reserving our opinion on that one. But
okay, I have a question about that.
Sure.
Is the deposition, the boundary deposition in an impact, does that also fall on the impact crater?
Yes.
Right.
Fact,
so right near the crater, you should have this boundary as well, just like you find at all these, like the KT boundary. It goes all the way up into the crater. Is that correct?
Well, yes and no. Obviously, if you have a huge impact into the land, right, or a shallow sea, you're going to have a tremendous amount of ejecta thrown up. And that stuff is going to go up, and depending upon its proximity to the epicenter, which will determine the force with which it's ejected, combined with the mass of the specific pieces, will determine how far that apron of ejecta will fall. Now, a lot of it will fall back into the crater itself. Yeah. So typically what you'll see is that as the crater form is gouged out by the impact, the explosive impetus of the impact, the heat of it will melt the glacier bottom, just like the KT boundary crater is vitrified. The surface is vitrified, and then overlying that is the breccia unit. The breccia unit is basically the broken rock,
crushed rock,
fell back into it, right? Now that stuff is also going to form this apron spreading out around the actual impact site. You can see that out at Meteor Crater by Winslow, Arizona. There was a debris apron that spread out, and of course, as you move further away from the crater, the size of the breccia diminishes. Obviously, right? The bigger stuff, just like in Meteor Crater, you're going to see these big old blocks, that are the size of a SUV and stuff sitting out there, but they're not, a mile or two away. They're sitting closer to the rim of the thing, right? So, yeah, no, I go back and ask me your question again, Kyle. I don't know if that
I was
really...
just the question was based on does the deposition, like we would see in the boundary layer, happen in and immediately around the crater as well?
Well, probably.
Or is that going to be so much different? Is it going to be more turbulent, more full of other things,
well,
harder to
again,
detect?
You're looking at so many variables there, but as a rule, there will be, like in the case of the KT boundary layer, the iridium was deposited over the entire globe, over the entire surface of the Earth. Now, obviously, iridium sprinkling down on the oceans is not going to get preserved unless maybe the concentration is so great that it comes down and would form a layer on the ocean bottom. But I don't think so. But I could be wrong. But certainly, the iridium can be found. It'll form a layer on the surface of the ground. It's going to fall on the surface, and then that's going to eventually get buried. Now, before it gets buried and preserved, all kinds of things could happen to it. So you will not find it uniformly distributed about. Around the crater itself, again, it depends on what kind of impact proxy you're looking for. Now, iridium is going to be very, very small, and then you can go up in the range. You've got microspherules, and then you have microtektites, and then you'll have actual macrotektites, which are large enough to hold in your hand, right? And those also are likely the result of condensation directly from a vapor or liquid, probably a liquid. The splash of the stuff as it's going up, the heat has melted the stuff, right? And the impactor hits the ground in the tremendous thermal high pressure maelstrom of the impact. Continental target rock and elements, a composition of the impactor itself, become all mixed and jumbled together. So that stuff is thrown up in the atmosphere. So you think of this molten stuff being thrown up and then raining back down. And as it rains back down, it's forming these aerodynamic shapes. And, in Georgia, where the fall line transitions down near Macon, there's an exposure of the Eocene-Oligocene boundary from 36 million years ago, when there was a great impact that now whose crater lies on the bottom of Chesapeake Bay. And when that impact occurred, again, you had this tremendous explosion and this uplifting of all of this material, molten material, and it's spreading out and raining back down. So it rained down over most of the state that is now Georgia. In fact, I think they're finding those tektites, the Georgiites, as they're called. I think they found them in Cuba. So it's reaching that far. Now, that stuff rains down on the ground, and now that's 36 million years ago. So in the subsequent 36 million years, that layer gets buried under perhaps many feet of sediment, right? So now what happens at the fall line is what's normally buried under many feet of sediment, there's a there's a topographical differentiation there that is exposing these various layers going back to the Eocene-Oligocene surface layer, and it's exposed. So basically what you do is after a heavy rainstorm, you go down there, and if you know the particular strata, how to find it, and it's not that easy to find. I've been down there with on a couple occasions with Ed Albin, who wrote his, he's a professor of geochemistry and astronomy at the Fernbank Science Center. I've accompanied him on a number of field trips out to look for impact proxies and also to study some of Georgia's Carolina bays. Anyways, he's an expert at identifying this hard to identify layer. So if you know where it is, you go down there, and I think that the tektite collection they have over at the Fernbank Science Center was collected in that way. Heavy rainstorm, basically these things will kind of wash out. of
They
the
roll out.
appropriate layer, and then you basically just have to in the dirt and mud. You look for them. Once you found a few, you kind of know what you're looking for, and you're going to pick up a lot of false leads. But then you'll pick up 10 or 100, and then there'll be a tektite. So that's the deal there.
Let me add something in on Kyle's question there. A lot of the impact sites that are known across Canada that were prior to the Ice Age are now lakes. So quite a few of the places that we would look at as being potential impacts from an object, not airburst over the ice sheet, but impacts into the ice sheet are probably now lakes.
Yeah.
Full of water.
So we'd have to core down into those, and actually we've got a list of lakes that we'd like to core and see what those look like, and see if there is some sort of YDB evidence in the bottom of those lakes.
Well, and speaking of lakes, next episode we're going to be looking at two lakes, Lake St. Jean and Oak Lake, to try to better understand this, because each week we're going to try to bring in a few dots. And right now the dots are still pretty chaotic. Our goal here, hopefully, is that at some point in this array of dots, in each dot is an element of evidence, if you want to look at it that way. And then at some point we'll be connecting these dots and to see if a coherent pattern emerges that we can go, all right, we're nailing this culprit here. Because whatever the culprit was, the critics have referred to it as a Frankenstein monster, almost with the implication that, well, if it's a Frankenstein monster, it's a fiction of imagination. I would go, yeah, I agree with you. It appears to be a Frankenstein monster, but this monster is no fiction of the imagination. This monster is very real.
It's alive.
And we are trying to identify this monster and describe this monster, and then try to determine, is this monster extinct, dead and gone, or is this monster still around, or maybe perhaps the offspring of the monster?
So I have something I'd like to share. Like, once we finally do connect the dots, we're gonna look like this guy.
Let me see that guy.
Connecting the dots.
That makes sense now to him.
And I have something to say too. So really, 4 minutes and 45 seconds after I say 5 minutes, you ask a complicated question like that. I just don't.
I'm guilty. I know. I finally had a good question.
Yeah.
Maybe it was. I don't know.
No, it was a great question and a fantastic answer, but we are out of time. So thank you guys very much. And ladies and gentlemen, you know how to get a hold of us. Everything's in the show notes. See you guys next week. We got to go.
Thanks,
right now.
Got to go right now. Can't delay another second.
That's right. No, it is. We are over time. Brad will get mad.
I'm not going to get mad. I just pinch out a few of the things that I say.
Pinch out a few things.
Well, next week though, we're going to pretty much give Mike the floor for the whole time, and I'm going to sit back.
It'll be a silent hour.
Well, I've been listening to the shows, and I think it's, the show notes are so extensive that I think that it's better just to say everything's in the show notes.
Yep.
As I go through, I'm like, I like that better than us rattling off a whole bunch of stuff. Everything's in the show notes. So.
Well, and we
and that lets you talk. That lets Randall talk almost all the way up to the very end of the show and have it all be content. So.
Wow, good.
Yeah. Good. But I was starting to say several people have responded about the trip into Northeast Alabama.
Yep.
We're getting lots of amazing correspondence and questions, and now people inputting scientific papers. So
yeah,
the website, we're going to have multiple email addresses so we can help sort these things out, because it is quite overwhelming how many people are responding, and that's a great thing. But we're going to have some different email addresses so these can be sorted out and people can inquire directly about tours or input information directly about research. So we're gonna be announcing that soon also.
I think it would be cool to have a forum on the website too. I mean, I know that would be a pain to administrate, but if there was a forum where all these people could talk to each other, That's a big help, because then instead of everybody trying to get a hold of Randall,
Correct.
they can all collaborate with each other, and it's they can talk to each other. So a forum would be good. It would just be tough to find admins.
The wants list for the website is long.
Right. Yeah.
Value for value, folks. You're a forum guy?
Again,
Send an email.
Yeah.
But we might not find it because there's too many emails.
There's so many emails.
All right, well, we can shut it down if we got to, but there's always more to say, and then we can squeeze in an hour and a half. All right.
Well, see, here's what I would like to see a field like this, and we're building our institute out there, our institute of cosmological, cosmographic, geocosmic research, where we're integrating all the modern cutting edge with the archaic sciences. We're integrating that which is above with that which is below, and putting it in a context suitable for the 21st century.
That would be so fantastic.
Yeah.
Wouldn't it,
Yeah.
though?
We're going to spend some time talking about that too, for sure.
Absolutely, we are.
There's plans in the works.
Plans are in the works. Yep. All right, guys.
Yep.
All right.
Next
thanks,
week.
Randall.
Hey, blast as
Brad,
always.
Mike,
Yep.
Good
Thanks,
night.
everybody.
cheers.